Okay, here we go. So on Friday, we were doing all this stuff with our power series and turning them into things that look geometric so we could point out the first term and the R value, and then we could write out terms, and everything was beautiful. Sometimes we're going to have power series that we can't write geometrically, but if we integrate something or differentiate something, we can then write it out as a power series, and then we could use it to predict functions. So we're going to look at, this is where we're starting in our notes. So hopefully you have your notes packet. This is where we left off if you were in third block. First block we got past this because remember we had 3 hours. So here we have a box of big stuff right here. Interesting. Where we're writing out a polynomial type function, and you can write it as a sum of a power series, right? Because there's x in there, and that's what makes it a power series and not just a regular series. This first term, a sub 0, is a constant, so what we can do is we can take the derivative of each individual term, and so that's what this represents down here. Of course, the constant goes to 0. Notice right here, this is x to the first, so we're just going to get the number in front, or the constant. If it's squared, we'd bring that power down, multiply it, and subtract 1, just like normal integration. Differentiation, of course. Over here, look at what we can do with our nth term. We can take the derivative of it. It's just the power rule. Bring it down and subtract 1. Another beautiful thing we can do is the integral. Yay! And the crowd goes wild. Okay, well, look at plus c, because when you integrate, you have to have that constant. You have to account for that. And you can integrate each term individually, and it's just the power rule. Look at that right there. And then here's an important thing to note, that the radius of convergence of a power series for the derivative and integral will be the same thing, but the interval of convergence may not be the same thing because the endpoints may or may not be included. So remember, we did all that work the first day where we checked if endpoints were included or not. It's possible that you have to check endpoints to determine if they're included or not. So it is time for us to try example 7. Here's how this is going to work. Not well I can see. Example 7 in your notes, which is asking us to find a power series for this function. Now, notice that function is not completely geometric, so we can't just identify what the R is and what the first term is. We have to make it look more like a geometric. So what we know is the integral of f of x. What? Need a dx in there. It's going to equal 1 over 1 minus x plus c. So what that tells me is if I take the derivative of this, does this look familiar? Does this look something we could write that as a geometric series? If I take the derivative of this, I'm going to get this guy right here. So if I can write this one out, I can then take the derivative of each individual piece, and I will have a way to represent this. This is exciting stuff, guys. So I'm going to do this, 1 minus x, and I know how to write that out as a power series. Is the first term 1? Is the R value x? So would it be 1 plus x squared plus x cubed? And there's my first 4. And if I wanted to write this out, plus dot, 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 3 dots, no less, plus, let's write out our nth term. That's just going to be x to the n, and then plus dot, dot, dot. And if we start this on 0, so for all n greater than or equal to 0, that's going to work, and it will represent this function right here. Well, I know if I take the deriv of this one, I will get, do this with me, think of this as 1 minus x to the negative 1, right? We'd bring down the negative. We'd keep the inside. We'd subtract 1, so that would become minus 2, and then times the derivative of the inside. Looky there. Do I have this right here? I do believe I do. All right, so I took the derivative of this side. Now I can take the derivative of each individual term. 1 goes to 0, and I'll have 1 plus 2x plus 3x squared plus, let's do dot, 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 plus derivative of x to the n. Don't we bring down the n? Keep the x, subtract 1, plus dot, dot, dot. Now let's check if we put 0 in here for our n values. That's going to cancel this whole thing out. Will 0 work? Well, to get that derivative, 0 works. Oh,